This new concept, closed set. Okay, so let us discuss its definition. Let XD be a metric space. Okay, suppose we have one metric space XD. This is our metric space XD. A set capital A which is subset of X is said to be closed if, okay, see what is its definition. Suppose we have some set A which is subset of X. So when we say A is closed, if its complement is open, then we can declare it as a closed set. If X minus A is open, okay. So what is definition of closed set? It's very simple definition. If complement of any set is open, we can declare it as a closed set. Okay, so let us discuss few examples. So let us discuss examples. Let Rd be a metric space where D is the usual metric. You are familiar with usual metric. Usual metric means d of xy is equal to mod x minus y. This is usual metric. Okay. So let us discuss few examples. First, A is equal to close interval 2, 3. So we have to discuss, we have to check whether this set is closed or not. Okay. So what we have, this is a real line R getting 0, 1, 2, 3, 4. So this is closed interval. That means it contains its boundary points also. So we have to check whether set A is closed or not. How to check? We will check its complement. If complement is open, we can declare it as a closed set. So let us find its complement. Here R minus A. So if you remove this closed interval from a real line, what will we have? We will have minus infinity to 2, minus infinity to 2, this part of interval getting. So I have written open interval since point 2 is here. 2 is present in A, so it will not be in its complement. Union, that part, okay, so that means 3 to infinity. So complement of closed interval 2, 3 is minus infinity to 2 and 3 to infinity. See, these two intervals are open intervals. So that's why these two sets are open sets. And we know that arbitrary union of open set is open. So that's why this one is open set. Here R minus A is open set, getting. So therefore A is closed set, getting. So this is one example of closed set. You can make a screenshot of it. After that we will discuss few more interesting examples. So let us discuss second example. B is equal to open interval 2, 3. So this is a real line 0, 1, 2, 3, 4, minus 1 here getting. So see 2, 3, but this is open interval. That means this interval does not contain its boundary points 2 and 3. What will be its complement? Can you tell me? Then R minus B. So R minus B will be, so that means we have to remove that interval only 2, 3. So we will have minus infinity to 2 and 3 to infinity. So we will have here minus infinity to 2, but I will write here closed interval because 2 is not included in set B, so it should be in its complement. Union 3 is also not there in B, so I will add 3 to infinity. So clearly these two sets are not open, getting. So these are not open intervals, so that's why these two sets are not open, so their union cannot be open set. So that means simply here R minus B is not open. So complement of B is not open, so therefore B is also not a closed set. So therefore B is not a closed set. Let us discuss one more example, set C, which is equal to singleton 5. In a set, we have only one element, that is 5, and we have to check whether this set is closed or not. So I will show you, suppose 0, 1, 2, 3, 4, 5, 6 and so on. So only 5 element is there in a set. So then what will be its complement? R minus C is equal to, if you remove 5 from a real line, you will have a complement, that means minus infinity to 5 union 5 to infinity. You are getting all points which are less than 5, all points which are greater than 5, only 5 is removed. So that's why we have these two intervals, minus infinity to 5 and 5 to infinity. But see, both intervals are open intervals. So that's why these two sets are open sets. And arbitrary union of open set is open. So that's why R minus C is open set. Here R minus C is open. So that means complement of C is open. So that's why C is closed set. Therefore, C is closed set. Okay. You can make a screenshot of it. We will discuss few more examples. So the next set is Q, set of rational numbers. We have to check whether this set is closed or not. So obviously we will find its complement. Then R minus D, which is equal to R minus Q. See, other than rationals, that means obviously we have a irrational number. So this is nothing but set of irrational numbers. Irrational numbers. See, set of irrational numbers is not open. Okay. See, but R minus Q, that means set of irrational numbers, is not open. So that's why Q is not closed. See, its complement is not open, so that's why it is not closed. So it is closed only if its complement is open. Getting? So let us discuss one more example. Fifth example. 5. Empty set. We have to check whether it is closed or not. See, then I will find its complement R minus E, which is equal to R minus 5. If you remove empty set from any set, you will have a original number, just like 0. Empty set just like a 0. If you subtract 0 from any number, you will have a same number. So R minus empty set, it is equal to R. And R set, R means complete real line, which is open set. But R is open, so that's why what can we declare? Therefore its complement. Okay, so R is open, its complement is 5. So therefore 5 is closed. Getting? So in this way we proved 5 is closed. So some examples we have discussed here. You can make a screenshot of it. After that we will stop. Thank you. Bye bye.